We just fit a regression line. What if somebody comes and challenges our regression line? What if someone says the regression line that you have found is wrong? The coefficients that you got, beta naught and beta 1, are wrong. My regression line is y equal to some 2 plus 3 into x. As simple as that. That's it. That is my regression line, and it is better than your regression line. My regression line is best. If somebody challenges us, how do we actually try to convince that the regression line that we fit is best one, or how to find out the best regression line? How good is our regression line? How do we find it out? There is a simple way. Let us suppose here we are trying to find the regression line between, or we just fit the regression line between promotional budget and number of passengers. If the promotional budget is 517,356, we already know the number of passengers were 37,824. That's what happened historically. We anyway fit the regression line. What if I substitute 517,356? If my regression line is really good, I should be getting the estimated number of passengers as 37,824. Because my regression line is best fit for our data. If I am fitting this value of x, the estimated value of y should be this. So let us find the estimated value of y given the promotional budget is 517,356. For the data that we already know, I am still estimating it. I found it 37,031 is the estimated value, whereas the actual value is 37,824. This looks like a fairly good estimate, in and around the same. So this is the actual value, this is the predicted value. There is some error we have made here. I mean, it's not really large value, but still there is some error. When do we say our regression line is perfect fit? The estimated value and the predicted value should be exactly the same, and the difference or the deviation between them is error. So you just take a point xy from the data that is already there, from the historical data. Imagine that we substituted or submitted the value of x in the regression line, then we got a prediction that as y predicted. If the regression line is a good fit, then we expect y predicted that is exactly to be same as the y value, or y minus y predicted. The actual value y actual minus y predicted should be 0. If it is not 0, whatever is the deviation, that is called as an error. At every point of x, we repeat the same. That I'm talking about just one point. If we repeat the same on the overall data at every point of x, then y minus y predicted values will get multiple of them, and some values will be positive, some deviation will be positive, some deviation will be negative, because in some cases we over predict, in some cases we under predict. That means we might get a prediction which is higher than y, we might get a prediction which is lower than y in some cases. So for a best line, y predicted and y actual, or y actual minus y predicted, should be 0. So if we take all such deviations, at least the overall deviation should be 0 for, or deviation should be less for a good line. Since some deviations are positive, some deviations are negative, then what we'll do is we will take sum of squares of all such deviations. So for a given regression line, sum of squares of all such deviation, if we consider, this should be really less for a good regression line. So if we are comparing two regression lines, maybe we have to look at sum of squares of errors of regression line 1, sum of squares of errors of regression line 2. The one which makes lesser errors is the better line. For a good model, SSC must be 0, that is like best model, or near to 0. The problem is standalone SSC will not make any sense. Sometimes you will say, yeah, this value is near to 0, but it is not actually. Let's take an example. For example, if SSC is 100, is it near to 0 or not? It is really high or small? We can't tell. Why? Because it is very less when y is varying in terms of thousands or millions. If you're dealing with millions and millions, right? Now like y is in 2 million, 3 million, 4 million. So a deviation of 100 or something like that is not really high. But if you're dealing with some fractions or small values or decimals, then a value of 100 is really high. So in some cases 100 is low, in some cases 100 is high, so we have to somehow bring in the variance of y or the value of y also into the picture. Standalone SSE is not the right way of looking or measuring the error. So what do we do? How do we find how good is our regression line? So here is what, like, try to understand this derivation. It's a small derivation that will tell us the goodness of fate or of a regression line. So here is what we said, SSE, that is y predicted, y actual minus y predicted whole square, sum of squares of error. This should be least for a given regression line so that we can call it as a good regression line. But we have to somehow bring in the variance of y into picture, because based on variance of y only we can tell whether SSE is higher or lower. So this is the total sum of squares or total variance in y, which is y minus average of y whole square. That is just simply the formula of variance. Total sum of squares, we can in fact finally rewrite this whole thing, and finally we can derive total sum of squares. The variance in y is finally divided into two components, that is SSE, unexplained variance, SSR, that is explained variance. What are we trying to do in this whole regression? We are trying to predict y. We are trying to predict, or we are trying to estimate whole variance, or we are trying to explain the whole variance in y. So during that process we are making some error, that is SSE, and we are doing it, in some places we are doing it correctly. So for an example, if you see this, let us suppose this is the actual value of y at this point. This is the regression line. At this particular point, using x, I can predict y as this one, right? So whatever is this between this predicted value and the actual value, that is dot, this is the error. Till here we did not make any error, so that is the regression sum of square. So the total variance in y can be divided into two parts, that is variance that can't be explained by x, that is error, variance or remaining variance or variance that could be explained by our model, okay, using the regression, that is SSR. It is known as, or simply the total variance in y can be told as variance that can't be explained or the error, and the remaining variance that could, we could successfully explain, that is known as sum of squares of regression. So for a good model, SSE should be really low. Or one more way of looking at is your total variance in y is SSE plus SSR, and we need to make sure that for a really good model, SSE should be minimum. Yeah, the error sum of square should be minimum. SSR, just think about it, SSR should be minimum or maximum. SSR should be maximum, because we know that total sum of squares or the total variance in y is nothing but SSE plus SSR. So SSE by SST, that is total sum of square, this should be minimum, almost 0, because error should be almost 0. If error is 0, SSR, that the explained variance or regression sum of squares, should be almost near to 1 or almost equal to total sum of square. So there is a specific metric or measure called R square, which is SSR, which is regression sum of squares by total sum of squares, or this is also known as explained variance. So unexplained variance, explained variance. For a good model, explained variance should be near to 100%. If you have explained 90% of the variation, good model. If you have explained only 50% of the variation in y using the model, not a really good model. So that is how we find out whether a model is good or bad. We have to simply look at the value of R square, which is the percentage of explained variation using the model. So for a given model, we have to look at R square to tell whether a model is good or bad. If somebody is challenging us that my model is better than your model, the first question that we should ask is, what is your R square value? If the R square value of that model is 60%, whereas R square value of our model is 80% or 90%, then we can definitely say our model is explaining almost 90% of the variation in the overall y. Then our model is better model than your model. Okay, so let's try to do this. We have already fit a regression line, number of passengers versus promotional budget. Let's try to find out what is the R square value. What we need to do is simply go to the model, then try to run the summary of the model. Simply run this. So this is our model. Maybe we can rerun it, and this is the summary of the model. And what is the R square value of our model? What is R square value? R square is 93%. Is it a good model? Yes, it is, because we explained 93% of the variation in the data in the Y variable. What percent of the variation we could not explain? Around 7% of the variation we could not explain using this model. Just for comparison, let's try to build one more model. We'll try to build a model for predicting number of passengers using different variable called intermetro flight ratio. If there are more flights between metro cities, do you think the number of passengers will depend on that ratio or not? For that, we'll try to build a model and see that what is the R square value of that particular model. What is the R square value of that particular model? It is just 25%. Only 25% of the variation can be explained by intermetro flight ratio. So if you are trying to predict number of passengers, the promotional budget is a better variable because we could find a better fit. In fact, looks like there is no relation between intermetro flight ratio and passengers as well. As the intermetro flight ratio increases, the passengers are not really highly increasing. So that is how we find out whether a model is good fit or not, looking at R square value.